Sure. All right, so we're looking at, the last thing we were working on is integration, and we were doing the traditional u-substitution. The big way of integrating things. I mean, we don't have a product rule, we don't have quotient rules, we don't have chain rules. What we have is u-substitution. So just remind yourself, integration. The integral of k du, the integral of k du is equal to ku plus c. The integral of u to the n du is equal to u to the n plus 1 over n plus 1 plus c, provided n does not equal negative 1. The integral of 1 over u du is equal to the natural log of the absolute value of u plus c. And then the last one is the integral of e to the u du is equal to e to the u plus c. So these are the integral rules for the traditional u substitution. And number one, you let u equal to inside the parentheses. Number two, you let u equal to exponents on e's. Number three, you let u equal to the denominator if it doesn't have a power. And number four, the catch-all phrase. This is the important part. You let u equal something such that when you take its derivative up to a constant, the derivative is also in the problem. So whatever you let u equal to, du, the derivative, that differential of u, has to be in the problem up to a constant. You can always manipulate constants around. So, pick up where we left off last time. Was this problem here? I've got the integral of negative 5 e to the 2x dx. The ultimate goal of u substitution is to turn any problem into a formula you have memorized. Okay? So, in this problem, what am I going to let u equal to? Well, it's the integral of negative 5 e to the 2x dx. Well, one, I don't see any parentheses. Number two, I've got an e. So with e's, I'm going to let u equal to the exponent. So here, u would be equal to 2x. Then I'm going to take derivative, du. The derivative of 2x is going to be 2 dx. You can always manipulate the constant for substitution purposes. I'm going to divide both sides by 2. That gives me 1/2 of du equals to a dx. So when I substitute, u substitution, this becomes integral. This was e. The 2x was the u, so it becomes e to the u. Negative 5 is a constant, and constant holds over. You keep your constants right there. The 2x was u, but the dx is going to get replaced with a 1/2 du. Now, next rule, after you substitute, your problem should turn completely in terms of a problem of constants with u's in there. And clean it up, which means I get to pull my constants where? Out in front of the integral. And it should turn into a formula that you have memorized. So this will turn into negative 5 times 1/2 is going to be negative 5/2, the integral of e to the u du. Now that's a rule we have memorized. So that becomes negative 5/2. The integral of e to the u is e to the u plus c. And again, doing the steps. I'm doing the same steps over and over and over again. What's the last step with u substitution? Back substitute. The original problem was in terms of x, therefore your answer's got to be in terms of x. So this will be equal to negative 5/2 e to the 2x plus c, and there is my solution. Let's take a look at this next problem. The integral of negative 5 e to the 2x times 2 minus 3 e to the 2x quantity cubed dx. Yeah, I see some e's in this problem, but more importantly, what do I see in this problem? Parentheses. In traditional u substitution, you let u equal to what's inside the parentheses. So here, I'm going to let u equal to 2 minus 3e to the 2t. Does that make sense? Inside the parentheses. Step 1, find u. Step 2, find du. And remember, whatever the derivative is, up to a constant that we can manipulate, the derivative should be in this problem somewhere. Let's take a look. Well, the derivative of 2 is going to be 0 because it's a constant. Minus 3 is a constant. It holds over. What's the derivative of e to a function? Well, the derivative of e to a function is e to the function times the derivative of the exponent. Chain rule. So this becomes e to the 2t times the exponent, which is 2. And what do I put it into this thing? We took the derivative with respect to what variable? T, so I got to tack on a dt. Let's clean that up. So du would be equal to negative 3 times 2 is actually negative 6 e to the 2t dt. That's my derivative. Now, up to a constant. Move the constant over because you don't care about the constants. Move the constant over, and you end up getting this. Well, I'm going to divide both sides by negative 6. That gives me negative 1/6 du is equal to e to the 2t dt. Do you see an e to the 2t dt in this problem? E to the 2t dt, there it is. So you know you're on the right track. So when I substitute, this will turn into the integral. This part was u. And what are you doing to this u? You're raising it to the third power. Negative 5 is a constant. It holds over. Constants just hold over. But the e to the 2t dt gets replaced with a negative 1/6 du. So I'm literally substituting in for the e to the 2t dt is where the negative 1/6 du comes from. So u-substitution. And when you do the appropriate substitution, it should turn into, one, a problem with nothing but u's, du, and some constants, and clean it up, and it should turn into a formula that you have memorized. So this is equal to negative 5 times a negative 1/6 becomes 5/6. And I pull that constant out front. The integral of u cubed du. It's the famous power rule. The integral of u to the n du is u to the n plus 1 over n plus 1 plus c. So this is equal to 5/6 times u to the 4 over 4 plus c. Clean that up. That becomes 5 over 6 times 4 is 24. U to the 4 plus c. And what's the last thing you do to u substitution? Back substitute. So your final answer is going to be 5 over 24 times u, which is 2 minus 3 e to the 2t to the 4th power plus c. Just replacing the u with the original, what you let u equal to. And there is my solution. Question? Yeah. Okay. That was you. All right, so that got substituted for you, and it's being cubed, right? So that's where the u cube came from. That negative 5 is a constant. Constants will hold over. You can go, typically goes out front, but I just held him right here, and then eventually I put him out front. So the negative 5 just held out. What was left was this e to the 2t times dt, right? And e to the 2t times dt gets substituted in for the negative 1/6 du. So, and when you substitute means replace means these guys are gone, and I got that negative 1/6 du in its place. And then I cleaned it up, and it turned into a formula that I have memorized. Integrate it, and then back substitute, and this is the classic technique of u-substitution. Take a look at this problem here. Now, let's talk about steps, because I'm trying to give you guys steps that work every time on these u-substitutions. If you notice, the steps that I did was number 1, find u. Number 2, find du. Number 3, move the constant to the other side. And then number 4, substitute, clean up, integrate, and back substitute. That's what I'm doing every time. Let's go through those steps again. Look at this problem. I got integral e to the 3x minus 9 times 3 dx. Tell you what, see that 3 right there? I'm just going to pull him out front. I'm going to clean this guy up. This becomes 3 times integral e to the 3x minus 9 dx. Because I want to do the traditional same steps every time. So, step 1, I got to find u. Well, looking at this problem, I'm integrating 3 times e to the 3x minus 9 dx. With the classic e, what do I let u equal to? The exponent. So I'm going to let u equal to the 3x minus 9. That means du is equal to, what's my derivative? Derivative of 3x is going to be 3, derivative minus 9 is 0, dx. You always plug the d, whatever the variable, whether it be x's or d's or whatever letters you guys happen to have. Number Step 1, find u. Step 2, find du. Step 3, move the constant to the other side. I'm going to divide both sides by 3. So I get 1/3 du is equal to dx. Number 4, substitute. 3 is a constant being multiplied. It holds over. The integral, this function was e, but the 3x minus 9 was u. So that becomes e to the u. And the dx, in this case, that's the only thing that's left over, is going to get substituted for 1/3 du. Step 5, clean them up. Does that make sense? Substitute. This 3 stayed out front. It was a constant, right? This was e to the u. That was my function. You can't change the s of function, but u was the exponent. But the dx, I replaced with that 1/3 du. Now, pull all your constants together. But this is kind of nice. What's 3 times 1/3? 1. So they pretty much cancel there. That leaves you with the integral of e to the u, du. Step 5, integrate it. It should turn into a formula that you have memorized. What's the integral of e to the u? E to the u plus c. Okay, the integral and the d go away. You get the actual function, whatever the proper operation is, with 4 steps there. 4 rules. Integral of constant du is constant times u plus c. Integral of u to the n du is u to the n plus 1 over n plus 1 plus c. Integral e to u du is e to u plus c. Integral 1 over u du is natural log absolute value of u plus c. It's going to turn into one of these 4 problems here. Integrate them, and then what's step number 6? What's the last thing you're going to do? Back substitute. Get your answer. So this would be e. U was what? 3x minus 9 plus c. There's my solution. U-substitution. Does that make sense? Questions? Now, section 6.3. The definite interval. All right, so thus far, we have looked at what we call indefinite integrals. Now we're going to look at the other guy. So I wanted to compare and contrast what's going on. With an indefinite integral, our indefinite integral was this guy here. The integral a little f of x dx. And what was our rule? When you integrate a little f of x, what do we end up getting? This is a notation here. You get big f of x, and then what? Plus c. A definite integral, something extra is being added. It is this. It is the integral from a to b of f of x dx. You have bounds on this thing. That is called a definite integral. You're going to have some numbers on the bound. This is called the lower integrand. This is the upper integrand. The lower bound and the upper bound. Okay? Now, there's a little extra step involved in this, but it's going to be a numerical operation. So when you integrate a little f of x, you're going to get big F of x. Okay? You get the antiderivative. But then you're going to put a little line behind him. This is called the fundamental theorem of calculus, with a little a to b. This notation goes from a squiggly integral, elongated s, to a straight line from a to b, and it goes instead going, and the integral is in front, the straight line comes into the back. And then again, this is called the fundamental theorem of calculus. So you know it's important. There it is, fundamental theorem of calculus. What you do is you evaluate, plug in to upper bound, that will become a big F of b, minus plug in lower bound, big F of a. And when you're done with this thing, you're going to get a numerical solution. It's going to be a number. Now we'll get into the next section. This number is going to represent this idea of area under the curve, but wait on that. We'll get to that later. But you're going to get a numerical value. When you do an indefinite integral and you integrate it, you'll get a functional answer, plus c. Geez, Dr. Taylor, what happened to the plus c? Let me explain. When you integrate little f of x dx, you're right, you're going to get big F of x plus c. Then you plug in top bound. You'll get big F of b plus c. Then minus plug in the lower bound. Minus big F of a plus c. Distribute the minus, you get plus c minus c. What's plus c minus c? 0, because the c's cancel. And because the c's cancel, well, why write c at all then? So we don't, when you do a definite integral, we don't write the bounds anymore. Does that make sense? So, this is a definite integral, and when you get a definite integral, you're going to get a numerical value, a number for a solution. When you have an indefinite integral without numbers on the bound, you're going to get a functional answer plus c. So the difference between a definite and indefinite integral, okay? Now, with this stuff, there's going to be some properties with this, but this is the main property right here. When you integrate a little f of x dx, you get big F of x evaluated from a to b. Fundamental theorem, plug in top at big F of b, minus plug in bottom big F of a, crunch it out, and you get a numerical value. Okay. Now, one of the operations, the purpose of this is to get, this is going to be a formula, it is called the average value of a function f of x over an interval a to b. This average value is going to be equal to, now let's think about this for a second. What exactly is an average value? When I ask you guys to average your grades, what do? We talk about your test grades, even though you're about to get your last test real soon here. It's going to be on the computer this afternoon. I'll turn it back next time. How do you find your average of your grades? What do? You add up all the grades, and then you divide by the number of grades, right? All right. That formula, when you look at a function over a particular interval, so this is the idea. Here is from A to B. And here is the function. It goes down here, comes down here a little bit, and then whoop, goes up. Okay. So I got a nasty looking function, but here's f of x. Where do you think the average value is? When I talk about the average value is pretty much where's the average y coordinate? That's what I'm really asking. Well, look, for most of this interval, the average of your y coordinates you got is down here someplace. Does that make sense? So it's going to be down here, but right here, all of a sudden, the function took a big jump to the top. So you got some really high-looking functional values up here. That's going to pull the average up. Does that make sense? So right about here is where your average value is going to be. And it's a number, and it represents basically, on average, between A and B, where is the y coordinates averaging out at. That's what it is. And it's a formula, and that formula is this. It is 1 over b minus a, your bounds, times the integral from a to b of your function f of x dx. It is a pure formula, but it tells you on average what kind of y coordinate you're getting out of it over that interval between a and b. So they'll give you a function, and they'll give you an a and b. Let's do some examples, but before we do some examples, let's go through and get some of our terminology taken care of. So again, this is section 6.3, the definite integral. It says this. If a function y equals f of x is continuous on an interval between a and b, that f an integral of f from a to b is symbolized as, and the definite integral is this integral from a to b of f of x dx. So what's new is these bounds from a to b on your integral. The a number is called the lower limit of integration, and the number b is called the, we're not real hard on math people here, upper limit of integration. Okay, this is my integrand. The lower limit is a, the upper limit is b. For a function y equals f of x, non-negative and continuous on the interval between a and b, the area under the curve is given by this formula. The integral between a and b of f of x dx. This is what that numerical value, when you take the antiderivative, you plug in top minus plug in bottom. So let me give you a visual here. Here's between a and b. And let's say here's my function f of x. When I integrate from a to b of f of x dx, we know we're going to get a numerical value. It's going to be some kind of number. What this number is going to represent is if you take the function f and take a line where a is and drop it straight down back to the x-axis, and you take a point where b is on the function and drop it back down, the area under the curve that we talked about, the area under the curve is what this numerical value is. This is what that number is going to be. The area under the curve, from the curve back to the x-axis. That's what this thing is representing. So it has a geometric representation about what these numbers are. So, if a function y equals f of x is a continuous function on an interval between a and b, and big f of x is any antiderivative of little f of x dx, then the integral from a to b of f of x dx is equal to big f of x evaluated from a to b, which is equal to big f of b, plug in top, minus big f of a, plug in bottom. Now, there are some basic rules, properties of these definite integrals, and they're very similar to the property of integrals. And here's your first one. What is the integral between a to a of f of x dx? Well, the answer is going to be 0. Let me explain why. Two reasons. Number one, what I'm asking you, if you look at it from a geometry perspective here, what is the area under the curve of f of x between a and a? Well, it's 1 point. It's a dot. How much area is under a dot? There's no area under a dot. You've got to have length and width here, right? So there's no area under dots. That's why it's 0. Well, if you want to look at it also from the fundamental theorem of calculus perspective of the formula, we'll integrate little f of x. You get big f of x from a to a. According to the fundamental theorem, you plug in top minus plug in bottom. But the top bound is a, so f of a minus plug in the bottom, f of a. What's f of a minus f of a? 0, because they cancel. So there's two reasons why the thing is actually 0. But when you integrate over a point, you get 0. Now the other one is this one, and this one shouldn't be a surprise. The integral from a to b of a constant times f of x dx. Where do constants get to go when you're integrating? It doesn't matter if it's a definite interval or indefinite interval. Where do they go? Out front. So it'll be k times integral from a to b of f of x dx. And the other form that we played around with is, what about a definite integral? Integral from a to b of f of x plus or minus g of x dx. Well, when you integrate each term. And when you got bounds on it, it won't matter. That bounds will carry over. So this will be equal to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. And then you evaluate each function and calculate it out. And then the last one that we just talked about a few seconds ago, but again, drumming down in your notes, for a function y equals f of x, continuous on the interval between a and b, the average value is, and they call it AB for average value, is 1 over b minus a times integral from a to b of f of x dx. It is a formula for getting the average y coordinate. 1 over b minus a times integral from a to b of f of x dx. So let's do some examples. This first one is our classic video example off of hawkstv.com here. So, here we go. I want you to evaluate this definite integral. And they threw a big one at you here. The integral from 2 to 6 of 3x over x squared minus 3 dx. Here's the deal. This is a definite integral, but it's still an integral. And I don't care if it's got bounds on it or not. You're going to do the same thing each time. The first thing you got to do is you got to integrate it. So don't worry about the bounds. Just integrate it. So over here, I'm going to sit there and take my problem and just focus on the integral of 3x divided by x squared minus 3 dx. Do you have this formula memorized? Me neither. So which means I'm going to use u-substitution. What are you going to let u equal to? Well, when I have a fraction, I let u equal to the what? Denominator. Good. That's going to be x squared minus 3. Step 1, find u. Step 2, find du. What's the derivative? Du is equal to, well, derivative of x squared is 2x, derivative of minus 3 is 0 dx. Step 4, move the constant to the other side. I'm going to divide both sides by 2. I get 1/2 of du equals x dx. Step 3, substitute. This will turn into the integral. This is a division problem, and u was the denominator. You see that 3 right there? That was a constant. It holds over. The rest of it is going to be the x dx. And whatever you let u equal to, du better be in the problem up to the constant. The x dx is going to get replaced with a 1/2 du. And I'll just put the 1/2 du over here in the back. Clean it up. Step number 4, if you want to, clean it up. Put your constants together. What's 3 times a 1/2? 3/2. And we pull constants out front. So this turns into 3/2 the integral of 1 over u du, pulling all my constants out front. Step 5 is the big step. Integrate it. What's the integral 1 over u du? Natural log absolute x. This will be 3/2 natural log absolute value of u plus c. But we don't care about the plus. Well, then back substitute. This will be 3/2 the natural log absolute value of what was u? X squared minus 3 plus c. It's still all about integrating. But now, this is a definite integral. So you've got one more hoop to jump through. So, the integral from 2 to 6 of 3x over x squared minus 3 dx is going to be equal to your antiderivative, which is this guy here, your 3/2 natural log absolute value of x squared minus 3, but no plus c's on it because it's a definite integral. You put your bounds from 2 to 6. You still get the exact same answer whether it's an indefinite integral or a definite integral. You still got to integrate it. But with a definite integral, you don't put a plus c, you put a bar with your bounds from 2 to 6. And then you apply what we call the fundamental theorem of calculus. You plug in top, f of b, minus plug in bottom, f of a. So plug in top, this will be equal to 3/2 times the natural log of 6 is my top integrand, 6 squared minus 3, minus plug in bottom, that'll be 3/2 times the natural log of 2 squared minus 3. I'm just putting a little parentheses around it. Plug in top, the upper bound into your function, minus plug in the lower bound into your function here. Okay? Now, crunch out your numbers. This is equal to 3/2 natural log of what's 6 squared? 36 minus 3. 33 minus 3/2 natural log of what is 2 squared? 4 minus 3, 1. And one more thing. A little subtle note. We talked about him before. Note, what is the natural log of 1? This goes back chapter 3 stuff here. What's the natural log of 1 equal to? 0. So that part actually goes away. Go ahead and crunch your numbers out. So the actual answer is 3/2 natural log of 33. And for those people that just want to know, fine. 3/2 times, close parentheses, natural log of 33 is 5.2444761342. Does that make sense? Did I lose you guys anywhere? Yes, ma'am. Hmm? Oh, back into the integration stuff. Yes. Step one, I found u. Step two, I took the derivative of it. Derivative of x squared minus 3 is 2x dx. I moved the 2 to the other side, so 1/2 du equals the x dx. So when I see that x dx, that part's going to get replaced with 1/2 du. So this becomes 3 is a constant. It all holds over. This was divide. This was u, substitution. And then the rest of it, the x dx, gets replaced with 1/2 du. And a proper u substitution is constants will hold over, but the problem should not turn into the integral of u's with a du and some constants. No extra x's are left over. So then I put my constants together. 3 times 1/2 is 3/2. Constant goes out front. So this becomes 3/2 integral of 1 over u du. I integrate it. 3/2 natural log out to the value of u plus c. And then I back substitute. 3/2 natural log of x squared minus 3 plus c. But then when I go over here to the definite integral, the integral with bounds, basically, my function is the integral from 2 to 6 of 3x over x squared minus 3 dx. That's equal to the actual antiderivative function, which is your 3/2 natural log of x squared minus 3. No plus c's on it because you got bounds, and you draw your line from 2 to 6. And then you evaluate. Fundamental theorem. Plug in top, plug in 6, minus plug in bottom, and then just scratch out your answer. Look at this next guy here. And I'm going to show you guys some information you really want to know, but I'm going to hold my present for you guys until the end of class, because you're going to go, wow, this is awesome. So just wait for me. All right, evaluate the following definite integral. Find the exact answer or round to 2 decimal places. Okay, so fine, we're going to go decimal. So we're going to show you this is a numerical value. All right, this one is a straightforward problem here. You don't actually have to go and do u substitution or anything like that. This is a straight one. 8's a constant. Where do constants get to go? Out front. That'll be 8 times integral from 5 to 16 of 1 over x dx. Does that make sense? Now, 8 holds over. What's the integral 1 over x dx? Pure memorization from 2 sections ago. What is that? Natural log, absolute value of x, evaluated from 5 to 16. No plus c's on this stuff because you got bounds. Replace the plus c with a line from your bounds from 5 to 16. According to the fundamental theorem of calculus, you plug in top minus plug in bottom. So this would be equal to 8 times the natural log of the absolute value of 16 minus 8 times the natural log absolute value of 5. And the last thing, honestly, I'm going to do is this. What's the absolute value of 16, being it's positive already? 16. So you don't need the really absolute values on this one. So this would be 8 times the natural log of 16 minus 8 times the natural log of 5. And there's my answer, but they want it done as a decimal, so I'm going to go put it on the calculator here. 8 natural log of 16 minus 8 natural log of 5. Oops, lost 8 there. Natural log of 5. Type in exactly the way it looks, and I get 9.305206478. But they did say if you're going to put it in terms of a decimal, what do they say? 2 decimal places? Fine, I'll put the squiggly equal to 2 decimal places. What would that be? 9.3 what? 1. Does that make sense? At least you guys anyway. All right, let's look at the next one. The integral from 3 to 4 of 1 over 4x plus 1 dx. Is this a rule you guys have memorized? No, me neither. So I'm going to roll the problem over here and forget the bounds for just a second. And 1 over 4x plus 1 dx. I got to integrate this guy. It's not a rule I have memorized, so I'm going to use u substitution. With my u substitution techniques, I don't see any parentheses, I don't see any e's, but I see a denominator. So I'm going to let u equal to the denominator, 4x plus 1. Step 1, find u. Step 2, find du. The derivative, what's the derivative of 4x plus 1? 4 times dx. Good, don't forget your dx there. You took your respect to x. And then, step 3, move the constant to the other side. So I'm going to divide both sides by 4. And I'm going to get 1/4 du equals, his cancels, dx. Step 5, substitute. This will be the integral of 1 over 4x plus 1 was u, and the dx by himself gets replaced with 1/4 du. Literal substitution. Step 5, clean them up. this is equal to 1/4 the integral of 1 over u du. Then integrate it, turn it into a form you have memorized. What's the integral 1 over u again? 1/4 natural log absolute value of u. And then you back substitute. 1/4 the natural log absolute value of 4x plus 1. And you can put the plus c on here because this isn't an indefinite integral. It's an indefinite integral, so it doesn't have bounds, but that wasn't my original question. This work is just to figure out what the integral is. This is your antiderivative. Therefore, your problem, the integral from 3 to 4 of 1 over 4x plus 1 dx. Now we're talking about the definite integral. You get your antiderivative function, which is 1/4 the natural log of the absolute value of 4x plus 1. And then instead of plus c, you put your bound. Bracket from 3 to 4. Now you apply the fundamental theorem of calculus. Plug in top minus plug in bottom. This is equal to 1/4 times the natural log of the absolute value of 4 times 4 plus 1 minus 1/4 the natural log of the absolute value of 4 times 3 plus 1. So this is 1/4 the natural log. Now 4 times 4 is 16, plus 1 is 17. It's already positive, so you can just drop the absolute value, 17. 1/4 the natural log of 17, minus 1/4 the natural log. 4 times 3 is 12, plus 1 is 13. It's already positive, so you can drop the absolute values off of that guy. So the answer is 1/4 natural log of 17 minus 1/4 the natural log of 13. And so that's good enough. But if I put this on the calculator, this will end up being, parentheses around fractions, 1/4 the natural log of 17 minus parentheses 1/4 the natural log, of 13. And I end up getting 0.06706599966. But again, going with their 2 decimal place aspect, what's the answer? I'll put the squiggly equal to, what do they want? 0.07, 2 decimal places. Does that make sense? Look at the next one. This one I don't need u-substitution on because I can actually integrate it. So what is the integral from -5 to -3 of 5x squared dx? The first thing you're going to do is take the antiderivative. 5 is a constant. It holds over. What's the integral of x squared? Add 1 over add 1. What do you get? X cubed over 3. Basic rules. And then instead of plus c, you put your little bracket from -5 to -3. So, according to the fundamental theorem of calculus, you plug in the top number. This would be 5 times -3 cubed over 3 minus, plug in bottom, 5 times -5 cubed over 3. Now, just be careful of the numbers. This is equal to 5 times, what is -3 cubed? What's -3 times -3 times -3? -27. Negative cubed is still negative. Divided by 3. Minus 5 times, what's -5 cubed? -5 times -5 times -5. And if I want to do that on the calculator, so it's -125 by the way, but by doing a calculator, don't forget to put parentheses around it. Parentheses, -5 cubed is -125 over 3. Now clean up your numbers. 5 times a -27, and let me just back this thing down so you guys can see what I'm doing on the calculator here. 5 times -27 is -135 over 3. A -5 times a -127, 125, excuse me. -5 times a -125 is a positive 625. That becomes a plus 625 over 3. Notice you already have a common denominator, so add up your numerators. -135 plus 625 is 490 divided by 3. And 490 divided by 3 is, there's my answer, written in whole form there, but it is also 163.333333 repeating. So if I go for 2 decimal places, squiggly equal to 163.33 on the approximation. Does that make sense? Questions? This is the actual exact answer, 490 over 3. But if they wanted to 2 decimal places, that squiggly equal to is approximately 163.33. Take a look at this guy here. The integral from 2 to 5 of 6 plus 7 e to the x dx. Now, I know you're thinking u-substitution, but don't. There's no power on this thing or anything, but you do have 2 terms that are being added. So you can clean this up, and this will become the integral from 2 to 5 of 6 dx plus the integral from 2 to 5 of 7 e to the x dx. Now, integrate each one. So this would be equal to the integral of 6, a constant dx. What's the integral of a constant times x? Excuse me, screwed that up. What's the integral of a constant dx is going to be a constant times x. So the integral of 6 dx is 6x evaluated from 2 to 5 plus 7 is a constant, holds over. What's the integral of e to the x? Pure memorization. What's the integral of e to the x? E to the x evaluated from 2 to 5. Now applying your fundamental theorem of calculus, plug in top minus plug in bottom, but you got 2 sets you got to plug into here. Plug in top. This will be 6 times 5 minus plug in bottom, 6 times 2, plus, now for the 7 e to the x evaluated from 2 to 5, fundamental theorem, plug in top, that'll be 7 e to the 5 minus 7 e to the 2. So now you just want to kind of clean up your answer here. What's 6 times 5? 30 minus 6 times 2 is 12 plus 7 e to the 5 minus 7e squared. And then combine like terms, this will give you 7e5 minus 7e squared. They're not like terms, so there's not much you can do with those 2 guys, but you can add, the 30 minus 12. What's 30 minus 12? It's 18 plus 18. So there is the exact answer. And if I put that on my calculator for the approximate answer, this is going to be 7e to the 5th minus 7e squared. Yep, and I forgot to do one other thing, plus 18, plus 18 there. And I end up getting 1005.168721, but since they wanted at 2 decimal places, this would be 1005.17. Does that make sense? Let's take a look at this guy. The integral from 1 to 5 of -3 divided by the square root of x dx. I don't do square roots. What's a square root? Half a power. I don't do stuff on the bottom when they have powers. Stuff on the bottom when they have powers, you bring it to the numerator and make the exponent negative. So the first thing I'm going to do is clean this guy up. This will give you the integral from 1 to 5 of -3 times x to the -1/2. Square root is a half a power, x to the half. Bring them from the bottom to the top, makes x to the -1/2 dx. Now integrate them. This is a straight problem of x to the n dx. Integral x to the n dx is x to the n plus 1 over n plus 1. So this would be -3 is a constant, holds over. Integral of x to the -1/2, you add 1, that'll be x to the +1/2 over 1/2. No plus c's on this stuff, you put your little bracket evaluated from 1 to 5. But before I plug in top minus plug in bottom, I'm going to clean this guy up. When you divide by a half, how do you clean that up? Divide by a half, you invert multiply by the reciprocal, and that gives you what? 2 over 1. And 2 times -3 is actually -6 times x to the 1/2, evaluated from 1 to 5. I'm going to clean it up one little further here. a 1/2 power is a square root, so this is -6 times the square root of x evaluated from 1 to 5. Now, applying my fundamental theorem of calculus, plug in top minus plug in bottom, this gives me -6 times the square root of 5 minus -6 times the square root of 1. We'll clean it up. What's the square root of 1? 1, things you know from, I don't know, 5th grade or something. Okay, square root of 1 is 1. And then putting it together, this gives you -6 times the square root of 5. A minus makes it a plus 6. So here is my answer. If I put this on the old calculator for decimal purposes, -6 square root of 5 plus 6 is -7.416407865. So for that 2 decimal places, -7.42. Okay? Now, tell you what, I'm going to wait to do these 2 problems next time, and then we'll finish up this little section here, because it's good practice. But, well, I don't know, I got a couple more minutes. I want to show you guys something or other. All right, let's go back to that original problem that I did. Let's start with number 1 on the practice. You know, we have a very expensive calculator right here. I have a TI-84 Plus with a new operating system in it. And you can tell by your calculator what kind of operating system you got. So everybody, grab your calculator out, because I'm going to give you guys a huge gift here. Take your calculator out and turn it on. I want you to do this. Everybody go to Math, on the little button. Math button is right here. Math, and scroll down to number 9. You will see an F-N-I-N-T. Do you see him? F-N stands for function. I-N-T stands for integrate. Hit that button. Now this is what's going to happen if you got the new operating system. You got the little integral with the little bounds and your little function and your little d thing here. So let's just type in this old answer here. This is going from 5 to 16, the lower bound, upper bound, and then over arrow. My function is 8 divided by x. And then you got to tell what the variable is to the calculator. D, what is it? dx. And I hit the old enter on the calculator. Now it's a calculator, so it's going to give me the decimal version of my answer. Merry Christmas. Which means I am showing you people how to cheat. This is awesome. What a great professor. I'm showing you guys how to cheat. No, I'm not. I'm showing you how to check your answers to make sure you don't make some bonehead, careless error. No work means no credit. If I don't see all this beautiful work, you get absolutely no credit, and I take off extra points for making me look at crappy decimal answers without the work on it. Look at this one right here. Let's do this one and see if we can get the same answer. Oh, you got the T83. May I borrow it? Yeah, you do have it. I'm just going to show you where it's at. All right, this is a TI-83. If you happen to have the TI-83, no worries, but you have the old operating system. So if you go to Math number 9, this is the new operating system, the integral with the set on it. The old operating system, here's your programming keystrokes. You got to type in the function. What's my function? 1 divided by parentheses 4x plus 1, close parentheses. Type in the function and then hit comma with the old operating. Comma is right above number 7. Then you got to type in the d part. What's the variable? X. So this is the function dx, and then you hit another comma. Then you type in low bound and upper bound, because you always read an integral from low to high. The lower bound is 3, comma. The upper bound is 4. So this is your keystroke for the program on the old operating system. Function, comma, x, comma, low bound, comma, upper bound, close parentheses. Now, you hit enter, you get that. Let me try it on this one. It's the integral from 3 to 4 of 1 divided by parentheses with your denominator 4x plus 1, then over arrow dx. And you notice you get the exact same answer, which just so happens to be the answer that we actually got when we did it by hand. Does that make sense? So if you got the old operating system, you can still do this. Do this, but no work is no credit. All I'm doing is showing you guys how to use your calculator to be able to check your answers. Show your work first. We'll finish up the last few problems next time and then move on into section 6.4. So see you guys then.